Our next speaker is Dr. Peter Frise. He is CEO and Scientific Director of Auto 21, Network of Centers of Excellence in Canada. So let's welcome Dr. Frise.
Well, I'll say what everyone else said. It's really a pleasure to be here, but it really is a pleasure to be here because Italy's a beautiful place. Milano is a beautiful city, and it's a really interesting group of folks here, so it's really a pleasure. I'd really like to thank Bob Kiggins, Dan Nagy, Jack Harris, the folks at Poly di Milano, and of course Thomas, our talented moderator here, for everything they've done to put this session together. Although I will say to Thomas, the car is going to change more in the next 10 years than it has in the previous 50, and I'll show you why. The dipstick may go away, but lubricating oil won't, and I'll show you why too. Okay, so let's talk about the global vehicle industry, what drives it and so on, and what's probably going to happen in the future, but I just say probably is just one guy's opinion on this, because there's a lot of big open questions in that sector right now. Okay, so if you look at the future car, what are the key influences on what the future car will be like? Well, it's really what people want to buy, what government will demand, because it's one of the most regulated industries in the world, and what industry imperatives sort of drive things. What people want to buy is basically a better value proposition, and value is best defined probably by the ratio of performance and price. But you have to define performance the way you want it. Some people want to haul a big boat, some people want to go around corners fast, some people want a really cool sound system, and so on. But that ratio of performance over price is really what drives consumers. The government demands environmental performance, safety, and good jobs. The auto industry is one of the largest providers of high-quality employment in the world, in the countries where it operates. And of course, what industry has to do is build the highest quality products at the lowest possible cost, and they have to do it fast, and they have to be really flexible, because priorities change within the market, basically with the price of oil, and it goes up and down like crazy. And so the companies have to respond to that. So let's talk about energy for just a minute. What drives energy use in cars? And it doesn't matter what kind of powertrain you have. This is just grade 9 physics. Vehicle weight dominates at low speeds, which is where most driving is done, especially in Europe. I've just come from England, and I can tell you that I'm an expert driver at low speeds now because I was on British roads. But it dominates at low speeds around cities. That's vehicle weight. Vehicle aerodynamics dominates at high speeds. And driver behavior is important at all speeds, and that really includes obviously driving habits, but also maintenance of the car. We did a study about 10 years ago in Canada. We found that about 80% of the automobiles on the road do not have properly inflated tires, 80%. So it's really quite something. So what this drives towards, and you can sort of see this in the newspapers, is lighter, sleeker vehicles with energy-efficient onboard systems. And we call those hotel systems, the heating, ventilating, air conditioning, all the stuff you have to have in a car because there are people inside it. But that's going to be tough because you've got to balance all that with vehicle safety. And in general, bigger, heavier vehicles are safer than lighter, smaller vehicles. And yet bigger, heavier vehicles use more energy, so they've got some very difficult and interesting engineering challenges. And of course, those are the same sorts of challenges that Diane Chong and her group face at Boeing every day as well. So let's look at some progress here. This is 32 years of automotive progress. In 1981, I bought a brand new Ford Escort, which was a nice little car at the time. It weighed 1,100 kilograms, 0 to 60 in 15.1 seconds. That seemed okay at the time. It wasn't as fast as my motorcycle, but it was acceptable. And I got 23 miles to the gallon, which is really good because my dad's Pontiac got 11 miles per gallon, which is, a huge number of liters per 100 kilometers. A 2013 Ford Focus weighs almost a third more. Its 0 to 60 time is about half. So it must be making a lot more power somehow, but it gets 31 miles per gallon, which is 50% better fuel economy almost. But also, the Focus has fuel injection, cam phasing, airbags, ABS brakes, HID headlights, air conditioning, power windows, power steering, power brakes, power seats, heated mirrors, satellite radio, Bluetooth phone, And it starts every single time, and it goes and turns and stops better. It's quieter, it doesn't rust, and it costs less in 1981 dollars than the Escort cost in 1981. How the heck did they do that? That's called technology, folks. It's also called beating the heck out of your suppliers, but it's called really sharp engineering, and I'm getting around to education here, I promise. Sorry, I'm having a small malaria attack right now, so I'm just gonna get rid of my coat. I'm not kidding. If I pass out, just drop flowers. But this isn't good enough. This isn't good enough at all, because if you look at that graph, that's a graph of the CAFE regulations, corporate average fuel economy, and it's going to undergo a 100% change in 15 years between 2010 and 2025. Right now we're at 2014. They'll start building 2015 cars in the next few weeks. The 2016 cars is sort of a milestone point where the corporate average fuel economy has to be 35.5. Those, and I apologize for the US units, that's what everybody uses in the industry in North America. The fact is that those vehicles are locked in. The 2016 cars, they were done a couple of years ago. And the industry knows how to do that, and you're seeing all kinds of things to do with that. The 2025 fuel economy regulations, people don't know how to do that yet. That's 10 years away, but that's only 2 product cycles. 2. That's not very much. So those vehicles are going to be under active development within about 4 or 5 years, those 2025 vehicles, and they are going to be very different. You have to, I mean, this is Europe, so probably quite a few people drive very small cars, but if this were a North American audience, there would probably be almost no one in the room whose car gets 54 miles per gallon. But in 2025, the average car has to get 54 miles per gallon. Not the tiny little tin can. The average has to be that. And yeah, there's a bit of a range there depending on how big the vehicle is, but basically fuel economy has to double in about 10 years. And this is the problem, and this is a slide I got from Dave McShane of Ricardo. The problem is, and don't worry about all the long distance heavy duty stuff, if you look on the left at that vertical scale right there, I think this is a laser, this is the energy content per in kilowatt hours per kilogram of gasoline, diesel fuel, kerosene, etc. And this is biodiesel. It's up in the 10, 12 kilowatts hours per kilogram range. The problem is lithium-ion batteries are down in the 0 range. They're not quite 0, but they're pretty darn small. And even hydrogen, if you want to talk about fuel cells, at 700 bar tank pressure, which is pretty high, it's going to be hard to do that. It just really is. You're certainly not going to be pulling a boat. So that's the problem. Okay, so what are we going to do? Remember, weight dominates at low speed, and most people spend most of their time at relatively low speed. So we're going to optimize steel body shell construction. We're going to do some aluminum stuff. We're going to do some more steel with space frames, different format of design. We're going to be lots of optimization of alloys throughout the vehicle, to optimize crush performance for safety, to optimize welding for manufacturability, formability, and so on. And there might be some carbon fiber, sort of a body in black type structure. The problem here is low cost. The auto industry is a huge user of materials, and it's very, very, very cost sensitive. So it's very hard to see how a whole vehicle could be carbon fiber. There are people doing some great work on reducing the cost of carbon fiber, but it isn't easy. And as long as Diane and her mob keep buying carbon fiber at 30 or 40 bucks a pound, my folks aren't going to be buying it for $3 a pound, because she's going to soak it all up, and they're going to want to sell to her. So this is a lot harder than it looks, but people are working on it. I got this slide from Volkswagen, and you should see what fully optimized advanced multi-material space frame shell hybrid body structure design sounds like in German. I can't say it, but it's cool. Now, if you look at this one, this is what's happening. Now, this is a very high-end vehicle. This is a Land Rover, but they saved 900 pounds by switching to aluminum. Ford will be releasing the next generation F-150 pickup truck. They're saving 700 pounds. And this is in an industry that will climb all over its mother to save 1 or 2 pounds. And they're saving 700 just like that. But the engineers in the crowd will realize what a gigantic transformation it is to go from steel to aluminum. It's as different as making toast and making a full-course turkey dinner. It's completely different, and it's a very, very tough problem. It's hard enough in a high-end vehicle like this, but in a mainstream vehicle like an F-150, it's a big, big, hairy job. So this is a graph that shows materials use in vehicles between 1985 and 2010, and you can see that things really hardly changed at all. 2025, it's got to be different, very, very different. And this goes right to the heart of one of the points that Diane made. It's not good enough to just make parts out of new material that look like the old parts. We have to have people who know how to get the best possible performance out of these parts. How the heck do we do that? I'm getting there. This is another one of those things. This is a product that one of the big automotive suppliers is working with us on. It's called ACOS Division. It's basically some exciters that excite the glass and replace the audio speakers in the car. And this really works, and it works really well, and it saves a lot of weight, 14 kilograms, which is a lot, but it also reduces power consumption by 96%. And it sounds just as good as a regular stereo, and it makes the car much easier to build because you don't have to run wires all over the place and have speakers in the doors and all that stuff. So this is the kind of thing that's going to happen to the future vehicle. And so there's a big transformation has to happen. It's a huge opportunity to bring new technology to the future vehicle. Okay, so how are we going to do that? We're going to have to evolve our people to meet those evolving needs, and it's going to be a big, big, tough job. So how do we find the right people? And this is something I've been doing a lot of work on. It's not easy. It's really a combination of values, attitude, behavior, and fit. And if you have, if this is a little matrix of sort of attitude and skills, having good skills but a bad attitude is no good. That guy's going to leave, or you're going to ask him to leave. Having obviously poor skills and a bad attitude that's easy. Having poor skills and a good attitude may make that person possibly useful, but the people you really want to find are the people who have a great attitude, great values, behavior, and all that stuff, and they really fit, and you want them to stay. So how do you find those people in an engineering workforce? It's not easy. In the old days, this is kind of what the technical product development team looked like. You had a product engineer at the top who said, okay, we need a new door for this vehicle, and I want it to kind of fit here, and it's got to have a weight target of such and such and a cost target of such and such and so on. So there was sort of a conceptual design of the component, and the manufacturing engineers basically decided how to make it. The designer draftsman decided what the shape and the geometry of the thing would be, and the engineering analyst would make sure that it complied with all the specifications. The problem with all that is there's a lot of communication that has to happen back and forth horizontally through here, and there's a lot of opportunity for screw-ups and really some big messes, and some big messes did happen. One of the OEMs, I won't tell you which one it was, had the VP of engineering believed in freedom, so he had his he said to people, you can choose which CAD system you want, because he was assured that all of them could have good translation from one package to the other. Well, in fact, the engine and the transaxle bell housing patterns did not match. And so they couldn't mate the transmissions to the engines, which was a bad problem. So with the increased technical content, the need for faster product development cycles and cost reduction and all those sorts of things, and the outsourcing or downloading of design responsibility to the supplier base, which is really one of the other key themes from this morning, there's an increased need for much higher value from a given person. And so this is what the team is evolving to. There's this central resource. That person's called I call them a design engineer. They know about specification, compliance, and geometry, and they know how to plan a manufacturing program, and they use digital tools to do that in a big way. Now, sometimes they consult with experts on analysis problems or manufacturing problems, but basically everything passes through that design engineer. That's a much higher value-added person. It's probably a person with at least a bachelor's degree, if not higher. And so the day of the old-fashioned, community college-educated draftsman is, in my experience, kind of dying out a little bit. They're not bad. They're great people, but they just don't know enough about analysis and manufacturing plans to really be able to contribute enough value to compete in this world where things have to happen so much faster at lower cost. So that brought me to sort of coin a term called what I call the capability inventory of a company. And basically, it's kind of these three things: what your own people can do and what your own physical infrastructure can accommodate, plus what your suppliers can do. And that's really important, to extend your enterprise out there and make sure that you're dealing with your suppliers in a way that makes sense. And this goes back to what Goran Rus said this morning about the supplier base being critical in any extended enterprise. So how do we educate these people? How do we educate them? I started Canada's first program in automotive engineering in 1998. Before I did that, we did a big study of the skills needs for mechanical engineers. And it was very similar in many respects to the ASME study on product realization processes. What does industry actually want from young engineers? It turns out that hardly anybody said anything about sort of the technical skills. We're really good at teaching chemistry and physics and math and all that stuff. That's really good. What we're not good at teaching is how to communicate, how to work on a team, how to get along with other people, and in some cases, how to show up on time and do the right thing. And so it's, again, back to those values and fit. So when we developed our program at Windsor, we really focused very much on practice issues and on nuts and bolts issues. Even though our students, this is an accredited engineering program, we're not educating mechanics here. We actually took over a small elementary school that was abandoned by the school board and turned it into a big garage. And this is actually my company car. Just kidding. But we took over, and we had the kids in there working on a pretty regular basis with their hands. Their textbook for that course is a toolbox, because we found that very few young people these days had ever worked with tools. And to my way of thinking, it's impossible to design a good piece of machinery or a good product if you have no idea how it might be made and how it might be serviced. And this is a constant problem that we've run into. So Linamar gave us 100 of those small engines. Everybody gets one. They run it. They do a performance test on it. They learn how to measure the noise and the vibration and fuel consumption and so on. And then they strip it down, and we have all the manufacturing drawings blown up around the room on the walls. They make precision measurements and do tolerance stack-up calculations and all that sort of thing that people have to do on a daily basis. And in this way, we're creating that next generation of design engineers. And it's been very successful. I'll just give you a little commercial. I've got a couple minutes here, a little commercial about Auto 21. It's the largest research network in Canada. It's one of our federally supported networks of centers of excellence. We have 48 universities involved in the network. We support the work of about 230 professors across the country. All of the work is co-funded with industry. We support about 430 graduate students, and we have an annual conference every year. We just had a great conference in Niagara Falls, Ontario, and this upcoming year we'll have our conference in Ottawa, which is a very nice place. It's our national capital, of course. So I just will close with that. The host institution of Auto 21 is the University of Windsor. We're very proud of that. And everybody else has been throwing in a little saying, so I thought I'd throw one in too. And the one I chose is from my dad, Don Frise: "The harder I work, the luckier I get." And I think that's a good thought to end on. Thank you very much. One more thing, be sure and visit the Invest in Canada booth outside. Sandra Marchese and Michele Camulli are there, and they will be happy to talk to you about investing in Canada. It's a great place to visit. We have Anne of Green Gables, we have Mounties, mountains, the whole thing. Plus, we're an advanced manufacturing nation. Thank you.
Thank you very much. And again, I wanted to point out, so we talk about even on automotive, right? We're talking about engineers and so forth. One of the big areas is composites, right? Well, guess what? If you have some foreign object damage, I'm sure that so good Dr. Chong will also, basically say, yes, this is true, right? You don't repair it like you do a metal car. You don't go down to the body shop and drill a hole, pop it out, little Bondo, paint it and sand it. And it's the same thing. So it really affects the whole the whole ecosystem for the automotive sector when you're going to these new materials. And by the way, we all know these new materials, the composites, they're not homogeneous, right? They have directionality in terms of strength, and so we even have to think about that. Now, what's interesting, and one of my colleagues pointed this out, is we've lost that capability. It turns out if you look at 100 to 200 years ago, we thought about composites. Your most advanced engineers, which were in which business? Shipbuilding, built things out of wood, and we had to think about things in terms of grain direction. And when we went to plastics and metals, we forgot about that. We lost that technical capability. So again, historically, it's really quite interesting to take a look at some of these things. They do come back to haunt you.